Hey everybody, Mr. Judson here. So two things, I just want to make sure that we get this. First of all, an average rate of change, which I've abbreviated average rate of change, is always equal to the slope between 2 points. And we always want to find it that way. That'll never change, okay? So this is equal to the slope, between 2 points. Okay, and that won't change, right? Anytime we see average rate of change, that's what we're thinking. Just get an xy coordinate, get another xy coordinate, find the slope. The instantaneous rate of change, I always think of that word instantaneous as at a specific point, at that instant. This we're going to find with a derivative. Okay? They're both slopes, but this is a slope of a tangent line, this is the slope between 2 points. So an instantaneous rate of change is a slope found with the derivative. So we just want to keep those two things straight. Average rate of change, instantaneous rate of change. All right, what we're going to do for today is try and take more of a look at the problem solving aspect of calculus. It's a big deal in calculus. I've kind of ignored it up to this point, trying to buy us a little bit of time, but we can only ignore it for so long. So I want to remind you guys of the position function where you're throwing things through the air. And a lot of times in pre-calc we measure the height of that object. So what I'm going to say is this: a position function, or the height, with relation to time. So remember, when you throw something up in the air, as time moves forward, it's going to go up for a while, but eventually gravity will stop it, and then it'll begin to fall back down. Whether you throw it straight up or whether you throw it off this way, doesn't matter. We're measuring the height from the ground. And that's equal to 1/2 of gravity times t squared plus the initial velocity, that little sub-zero means in the beginning, times t plus the initial height. So gravity is equal to one of two things. It's either equal to a negative 32 feet per second squared, if we're dealing in the standard system, feet and seconds, or it's equal to a negative 9.8 meters per second squared if we're in the metric system. And a lot of times, people kind of struggle with what that really means. A negative 32 feet per second squared, really this is acceleration due to gravity. Okay? And what it means is, if an object is falling, its speed will increase in the downward direction by 32 feet per second for every second it continues to fall. Okay? So if I get up on a tall building and I drop something, in 1 second, well, first of all, when I first let go, okay, when I let go, there's a split second that it sits there and then begins to fall. So after 1 second, it should be falling at a rate of 32 feet per second, downward, okay? And then after the second second, it's now falling at 64 feet per second, because the rate at which it falls will increase in the downward direction by 32 feet per second for every second it falls. Okay? After 3 seconds, it would be 96 feet per second. That's how fast it's falling. So you think about somebody up on on top of a tall building and they let go of a ball, and it takes 5 seconds for that ball to get to you, and you're going to catch it, well, 5 times 32, that means it's traveling at a rate of 160 feet per second when it gets to you. Now, there's other things that come into play, like air resistance. You know, some things cut through the air better than others. If you took like a silver dollar and you spin it so that it's spinning as it falls, it will cut through the air very well. If you drop a pillow, that's not going to cut through the air so well. So there's air resistance will slow it down. But now we're getting into college physics, and that's a whole nother ballgame. You know, we're going to try and keep it simple. All right, v sub 0 equals the initial velocity. So if I just let go of an object, I let go, it's sitting there for a second, then it begins to fall. Well, not for a full second, a split second. Its initial velocity is 0. It's not doing anything. Now if I throw it up in the air first, because I want to get it as high as I can so that when it reaches the high point it falls even faster, well, my initial velocity is in the upward direction, so that's positive. If someone's thinking, no, you're better just to throw it straight down off the top of this building, because give it some initial speed, well, then it starts off with a negative velocity because it's going downward. Okay? And the initial height, or h sub 0, is the initial height. So if I'm standing on a 30-story building, it's about 10 feet per story, that's 300 feet, that's my initial height. Okay? If I'm hitting a golf ball that's sitting on the ground, the moment I hit the ball, if I want to measure its height, its initial height was 0 because it's on the ground. All right, so I got a fun story here. This happened a long time ago when my kids were little. We wanted to have some fun, so we found this bridge. It's over on the Olympic Peninsula, and we wanted to throw rocks off the bridge. And we started wondering, like, how fast are those rocks going when it hits the ground, the bottom? There was a river down there. There were no people. So we got these nice round river rocks, and we took them up there and we throw them off, and they go down. And if there's this one rock in the middle of the river, and if you hit that, then your rock explodes and pieces go everywhere, and it was so much fun. I don't know why some people think that's fun, but they do. So anyway, so here's let's do a little artwork. I've got this cliff right here. And here's the bridge. There's Judson standing up there with his rock. Getting ready to throw it off the bridge. Down here we've got this river is flowing through, a big old rock in the middle. So I'm trying to hit that. And the question was, how fast is that rock going when it hits the bottom? Well, I don't even know how far it is. So we had to play around with this equation a little bit. The first thing we did is we thought, okay, I'm just going to drop the rock and see how long it takes. Its initial velocity is 0, which means this right here would be 0 times t, so that's gone. I know what gravity is. I'm going to time it to see how long it takes, and I know when it gets to the bottom, we're going to call that 0. Okay, so we took this equation. The initial height equals, so it's a half of a negative 32, so a negative 16 t squared plus the initial height, which I don't know what that is yet because I'm standing on the bridge. I didn't have my tape measure or my angulometer with me, right? So, anyway, I let go of the rock and I time it. It took 3.6 seconds. I remember doing this. 3.6 seconds for that rock to get to the bottom and make a splash. Okay, back in those days we all wore watches, so we had time, stopwatch on there. So it took 3.6 seconds I'm trying to figure out the height, and I know when it hit the bottom it was at 0. So pretty easy to see what happens. We'll just square this times negative 16, and we'll move it to the other side, and we've got the height of that bridge. All right, so if I grab my calculator, get rid of everything. So I've got a negative 16 times 3.6, and I want to square that. And so there's what I got. So 207.36 feet. It's negative. Once I move it over, I've got 207.36 equals h. There's the height of that bridge. So we're throwing rocks off a 210-foot bridge. And so I want to know, how fast is it going when it hits the bottom? Okay. Now we're going to do this two ways. We're going to say, okay, what if I just let go of the rock? How fast is it going? So here's my position function. H of t equals a negative 16t squared plus 207.36. So we got to think to ourselves, how do you find something like speed or velocity? Well, miles per hour, that sounds like a rate of change, or a slope. How do I find a slope in calculus? Derivative, right? So I need to take the derivative of this and then see how fast it's going. So h prime of t is going to equal a negative 32t plus 0. So I really didn't even need to know this at this point. Okay? And I know it took 3.6 seconds for it to hit the bottom. So h prime of 3.6 equals a negative 32 times 3.6. And so let's see if I do the calculator real quick. Negative 32 times 3.6 seconds. There we go. 115.2 feet per second. So yeah, that's going pretty fast. You know, that rock is moving. Well, what happens if all of a sudden Judson starts calculating things in his head and he thinks, if I could throw a rock up as high as I could, then how fast would it be going when it hit the bottom? Okay? So I'm going to change my equation a little bit. And I'm going to say, okay, we're going to throw the rock up at, I don't even know what a decent speed, I don't know, 20 feet per second? Is that fast? Is that slow? Am I a wimp if I say that? I don't know. At 20 feet per second. Okay? That's its initial velocity, and it's going in the upward direction. So now my equation becomes this. H of t equals a negative 16t squared plus, because it's going up, 20t plus, what was it, 207.36? Yeah. Now it's going to take a little longer to hit the bottom now, right? Because I didn't just let go and drop it. It's got to take more than the 3.6 seconds. So let's say I throw the rock up in the air, somebody hits a stopwatch, and they're watching. It's got to go up, and then eventually it's got to come back down, and it falls another 3.6 seconds. So we've got this time right here that we have to add. I don't know, let's just say it took 5.4 seconds, okay? So we want to find the velocity at t equals 5.4 seconds. You guys go ahead and try that. So once again, I need to find the derivative. So h prime of t is going to equal, and you guys, this is really important. The moment you see this word, we have to think rate of change or slope whenever we're doing story problems. Find the derivative and then plug your number in. So h prime of t, again I've got, if I multiply by 2, I've got a negative 32t plus 20. Ball was in, or the rock was in the air longer this time, so I've got h prime at 5.4 seconds. I've got a negative 32 times 5.4 plus 20. And so I check that on the calculator. Negative 32 times 5.4 plus 20. Yep. And now it's moving at a rate of 152.2 feet per second. And the negative velocity just means it's going down. You want to include that sign, okay? Whenever we talk about objects flying through the air, the positive or negative velocity tells us up versus down, so it's important. Okay, so 152.8 feet per second. Don't forget the label. That's how fast that rock is falling now. So this kind of stuff doesn't just apply to rocks flying through the air or, other objects flying through the air, golf ball or baseball. It also applies to moving objects. And one thing that they love to do in calculus is they talk about a particle moving along a line. Got a line, there's this little particle moving back and forth. It's very common in calculus. Okay, but anything that's moving, if we're looking for a rate of change, its velocity, we got to think derivative. A car driving down the road, okay, and we've got an equation. So, cars at stop, it hits the gas, and we've got an equation that talks about how fast its position as it accelerates down the road. Well, if I want to know its velocity at a certain time, I got to take the derivative of that position function and then plug a number in. Okay. So one thing that's real common in calculus, we have a position function. I don't know why, but calculate to use s of t for position. I hate the variable s because it looks like a 5. I don't know what s has to do with position. I guess there is an s in it, but why not call it p of t? I don't know, but books don't do that. They always call it s of t. So if I want the velocity function, then I need to take the derivative of that, and so that would be s prime of t, which is equal to our velocity function, v of t. Okay, v for velocity, that makes sense. But the velocity is the derivative of the position function. They also talk about something called acceleration. So we've got an acceleration function. We just talked about a car that it's sitting there to stop and it punches the gas and is accelerating down the street. Okay, so what does that mean? It's like an object falling. Negative 32 feet per second squared, it means its speed is going to increase by so many feet per second for every second it continues to fall. Well, you can have an acceleration function for a car, or a baseball that's thrown, or a golf ball that's hit. It's accelerating the moment it's hit at a certain speed. Okay? And your acceleration function is the derivative of the velocity function. So a of t equals the derivative of velocity, or, okay, here's something new, the second derivative of your position function. When you put 2 tick marks there, it means take the derivative once, then whatever that is, do the derivative of that. Do it again. Okay? That's a second derivative. We just put 2 tick marks. If I put 3 tick marks, does that mean a third derivative? Sure, I guess. I don't think I've done that very often in calculus. I've never done it here at Wilson. But at PLU, when I went to college there, and you got into differential equations, did we ever talk about a third derivative? I don't know, 35 years ago, I can't remember. Maybe? But yeah, if there's 3 tick marks, then I would do that. Okay. This is about as far as we go with this. So you guys will get asked some questions today about finding the acceleration of something. And so when you do that, you just, whatever your position function is, you take the derivative and then do the derivative again. Okay? If I had to do the derivative of this again, it's just negative 32. All right, let's look at this from a different angle. So we're going to look at this a slightly different way. I'm going to talk about a cost function. Let's say in a business. What's the overall cost to produce so many items? And they go through and they figure out an equation to determine that. Or maybe your cost function is, what's the cost per item to develop something? You know, we all know that the more items you produce, the cheaper it becomes per item. If you're making 100 t-shirts, it's less expensive, the cost per t-shirt, than if you're just making one. If you're just making one t-shirt, you got to pay for the art design, you got to pay for the silk screening setup, and then you make your t-shirt, and you probably got like a $150 t-shirt, nicest t-shirt in the world, right? But if you make 500 t-shirts, then that cost that you spent to do the artwork and the silk screening setup and everything, you spread that out across the 150 shirts, so the cost becomes cheaper per shirt, all right? So what we want to do is we want to figure out what the rate of change is for this cost function when x equals 5. Okay? So they will tell us to find the rate of change when x equals 5. And I don't really know what 5 is. Does that mean 5 units, which could be like an entire pallet full of something? Does it just mean 5 items? You know, I don't know what that means. There's not enough information here. Okay, but for right now, we're just trying to find the rate of change when x equals 5. Okay, you guys try it. So even if I'm not sure what all this stuff means, I'm focused on this, rate of change. That's a slope. How do we find slope? Derivative. It's not going to change this entire semester. I'm going to keep on asking that question. So C prime of x, I've got to use a quotient rule. So I'm going to do low d high. Derivative of the high part is 8 less high d low, which is 1, all over low squared will go. Now, just as kind of a hint to make life a little bit easier, anytime I do a product rule and I know I'm going to plug a number in, I am not going to waste my time simplifying this. Right? It is so much easier just to get the number in and work with it than it is to try and simplify it and then plug the number in. So I'm looking at this and thinking that if I'm going to do C prime at 5, okay, 5 minus 2, that's 3 times 8, that's 24. Over here, if I plug in a 5, I've got 40 minus 1, that's 39. So I'm going to subtract 39. And if I put a 5 in here, I've got 3. Square that, you get 9. So this is going to be a negative 15 ninths, which as a decimal number, let me just check that real quick. Negative 15 divided by 9. So a negative 1.667, we'll call it. Or if you want to, a negative 1.67, if I'm talking about money, it's a cost, right? And a lot of times we'll get asked to interpret what that answer means. And so let me remind you of something that we've talked about before. whenever we have to interpret a slope, something is increasing or decreasing by a certain amount for, and I have to change things a little bit here because last year we said for each additional whatever. Well, in calculus, it's only for the very next whatever x represents. And so that word next is going to be really important to us. For the next of something. This is always whatever y refers to. This is always our slope or rate of change. And this is what x refers to. So what is y referring to? The cost. Right? So I'm going to go ahead and put that in here. Let me take all these things out. So the cost is decreasing by $1.67. Include the dollar sign there, because we're talking money. For the next, now here's where I get in a little bit of trouble, because I don't know what X represents. Is it a unit of items? Is it a single item? I don't know. I'm just going to go ahead and write in items. But I'm not really sure what that X value, that 5, was referring to that we plugged in. Okay? Maybe it has to do with the number of days we're producing this or the number of months. So our cost is decreasing by $1.67 for the next month that we continue to produce this item. Okay? I suppose if we're decreasing, that's a good thing with cost, right? Whatever it costs me to produce something, I don't want it to increase. I don't want that to go up. That eats into my profits. Okay? All right, let's try another one. All right, so this question is kind of a weird question, but we've got a rectangle, and the length of the sides here is growing with time. So that the size of the rectangle is changing, okay? What they want us to do is they want us to find the rate of change of the rectangle's area. Now, what rate is that area changing? You guys go ahead and try it. All right, so I know when I first asked that question, you're probably sitting there going, huh? But stop the video, think about it. Find the rate of change. That means slope, right? And slope means derivative. So what's the area of this rectangle? Well, we know that area equals length times width. And so what I want to do is I just want to find the derivative. Now, I could use a product rule here, but remember I told you, once we get past the product rule, if there's an easier way, let's do that. And so I think using the power rule would be a little bit easier. So I'm going to think of that as t to the 1/2. When I multiply here, I'm going to get, so let's see, this is not the derivative yet. So I'm going to get 8t to the 3/2, 1/2 plus 1, plus 2t to the 1/2. And I need to take the derivative of that. So that's going to be, if I bring this down and multiply, I'm going to get 24/2, which is 12. T to the subtract 1 from the exponent. Bring this 1/2 down and multiply, you get 1. Times t, subtract 1 from the exponent, you get a -1/2. And so my derivative is going to be 12 root t plus 1 over the square root of t. There's my rate of change. Now, if they want to say, you know, at what rate is the rectangle's area changing after 4 seconds, well, then we just plug in a 4 and see what we get. Square root of 4 is 2 times 12, that's 24, plus 1/2, 24.5 square units per second. That's the rate at which it's changing at that moment. And it's really important that we kind of get what we're saying there. Okay, so I just made up 4. There's nothing magical there. I'm just making up a number. So if I was going to do that, then I would say a prime at 4 equals square root of that's 2 times 12, that's 24, plus 1 over the square root of 4, which is 2, so 1/2. So I get 0.5. And we've got to attach a label to this. So area is always measured in square units. And it's a rate of change. Now think of it this way. dA over dt. How is the area changing per unit of time? Kind of depends on what units of time we're talking about. But what we're saying is, if this rectangle is growing, we are adding 24.5 square units per, I don't know what it is, per second, per minute, whatever, at that point in time. So the rectangle's getting big pretty fast, okay? Now if we want to say what happens when t equals 10, okay, I put in a 10 in here. The rectangle has gotten bigger, and so as it gets bigger, the rate at which its area is going to change is going to be growing even faster. So we would expect a larger number here, okay? All right, so here's a problem that I found in our book, and it'll make us think a little bit. Find derivatives. This is off page 130 in the book. In these exercises, use the graphs of f and g and let p of x equal f of x times g of x. So I think p is for product, since we're multiplying two things. Remember that box means fraction bar? So I just put a fraction bar in there. Q of x means f of x divided by g of x. Quotient rule, okay, or a quotient. And so what they're asking us to do is they're asking us to find p prime at 4. Let's just do that one for now, okay? I want you guys to try and find p prime at 4. How many of you guys are just staring at this going, Well, we're multiplying two things, right, for p. So if I'm going to do part A, I'll show you guys how to do this and let you try part B. I know that the derivative of p, let's see, since I'm multiplying two things, I have to use the product rule. So I'm going to take the derivative of the first times the second, g of x, plus, leave the first piece the way it was, take the derivative of the second piece. The thing I love about this question is it really forces us to think. Okay, we know product rule and quotient rule, but now we're being asked a question in sort of a different context, and can I think my way through it? And more importantly, this is huge, you guys, do I really understand what a derivative is? Do I really understand? We've said all along it's a slope, right? That doesn't change. So if I want to know what p prime of 4 is, that means I'm putting a 4 where all these x's are. So f prime of 4, g of 4, plus f of 4, and g prime of 4. All right, so what's the derivative of f at 4? So if I go out to 4, that's right here. Derivative is slope, so what's the slope of this line at x equals 4? Well, we're going up 1 and over 2, so the slope is 1/2. What's g of 4? Well, that's just a y-coordinate, right? Plug in a 4, what do you get back out of the function? So here's the function g. At 4, the y value there is 8. What's f of 4? Okay, plug a 4 in. What's the y-coordinate? That's 1. Times, what's g prime of 4? So derivative means what's the slope of the tangent line? So if I go to the function g at 4, we're right there. What's the slope of that tangent line? 0. So what does this whole thing equal? Half of 8 is 4. There's my answer. All right, so now that we know how to think, let's try part B. Find q prime of 7. Q is equal to this fraction, and so what I need to do is I need to find the derivative at 7. You guys go ahead and try. All right, so q of x is equal to f of x over g of x. So when I take the derivative of this, I have to use the quotient rule. So q prime of x is going to equal low d high, so that's g of x, f prime of x, less high d low, f of x, times g prime of x, all over low squared will go. Now plug a 7 in. I was going to say 4, but it's 7. So now plug a 7 in, and q prime at 7. So I got to think, what's g of 7? Well, here's 7. G is 4. G of x equals 4 at 7. So I've got 4. What's f prime of 7? Here's f. Go to 7. What's the slope right here? I'm going up 2 and over 1. So that would be 2. Minus, what's f of 7? Plug in a 7, you get 4. Same thing for both f and g. So 4. What's g prime? Okay, that's a negative slope. We're going down 1 and over 1, so that would be a negative 1. All over g of 7 squared. G of 7 was 4. We wrote it right here. So 4 squared. So now what I have is 8 plus 4. That's 12 over 16. Which if I simplify that, I would get 3/4. There's my answer. All right, kind of like that problem. Makes us think a little bit. All right, so here's our homework assignment. We're starting week 9. Wow, 9 weeks in. Time for report cards. Whoa. Week 9, page 120, we'll do 95 through 98 and 106. And on page 130, 65, 81, 83 to 85, 87, and then 115 to 117. I'm taking the last 2 sections that we worked on and trying to combine the story problems into one. I'm really doing that just, again, to buy us time. Instead of taking 2 days, I'll make each assignment a little bit shorter, and we'll try and accomplish this in 1 day. All right, that's it. That's all I have for you guys. Remember, Wednesday's Veterans Day. It's a day off, so no homework. And I will see you guys on Thursday. All right, take care.